The algebra of complex numbers. Before you work through this video, it's a very good idea you know how the imaginary number arose. If necessary, you should refer to this video which covers this topic. Thanks for watching this video and don't forget to like, subscribe to the channel and activate the notifications. It's very important to the continuity of this channel. We have already seen that the square of a real number is always non-negative. But in algebra, sometimes appears the square root of a negative number. It's clear that a negative number cannot have a real square root. So we need to extend the system of real numbers to a system in which we can find out the square roots of negative numbers. Such numbers are incorporated into the system of numbers by defining the square root of -1 as a new number which is usually denoted by I, or we can also write I squared is -1. A number containing square root of -1 is called a complex number. A complex number can be written in standard form as follows: z equals to a plus b times I. Z is the complex number. The letter Z is usually used to denote a complex number. A and B are real numbers. A is the real part of the complex number. B is the imaginary part of the complex number. I, or square root of -1, is the imaginary number. In meeting a new mathematical system for the first time, the concepts of equality, addition, subtraction, multiplication, and division need to be properly defined. And that is the purpose of the present video. Even if the definitions are fairly obvious, they need to be made without contradicting ideas already established in the system of real numbers, which complex numbers include. We can think of complex numbers as binomials of a sort. Therefore, complex numbers are added, subtracted, and multiplied just as we would any binomial. The only difference that we need to keep in mind is that I squared is equal to -1. When adding or subtracting two complex numbers, adding or subtracting their real parts and their imaginary parts separately. Let's see how it works. The sum of two complex numbers is made up of the sum of their real parts plus the sum of their imaginary parts multiplied by the letter I. The difference of two complex numbers is made up of the difference of their real parts plus the difference of their imaginary parts multiplied by the letter I. When multiplying two or more complex numbers, we complete the operation as we would with normal algebra. Pay attention. Multiply complex numbers like binomials, expanding the brackets and collecting like terms. Replace I squared with -1. Two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. If these complex numbers are equal, then the real part of the first must be equal to the real part of the second, and the imaginary part of the first must be equal to the imaginary part of the second. Before we do the division, we have to introduce the concept of a conjugate complex number, or simply complex conjugate. Let z equals a plus I times b be a complex number. Then a complex number obtained by changing the sign of imaginary part of the complex number is called the conjugate of z, and it's denoted by z bar. In short, the conjugate of a complex number is the same number, but with the opposite sign in the middle. Pay attention to the following examples. Conjugate complex numbers have a very important property. Pay attention. Let's multiply a complex number by its conjugate. When we multiply conjugates, we can use the distributive law or the difference of squares. Note that the i's disappeared, and the final result is a sum of squares. Pay attention to the following example. The i's disappeared as well. The product of complex conjugates is always a real number. This is what the conjugate is for, and we will use this property to do the division of complex numbers. When dividing two complex numbers, we multiply the numerator and denominator by the conjugate of the denominator. This process removes the imaginary number from the denominator. The m here is to make the denominator real, and hence we multiply numerator and denominator by the conjugate of the denominator. This is very similar to rationalizing the denominator of a fraction involving thirds. This result is not meant to be memorized. Rather, we should work through the multiplication or division in question and then simplify the result. In the last step, note how the fraction was split into two pieces. This is because a complex number is in two parts, the real part and the imaginary part. They are not supposed to share the denominator. To be sure your answer is completely correct, split the complex valued fraction into its two separate terms. Express the following as a complex number in standard form. Since our denominator is 1 plus I, its conjugate is equal to 1 minus I. Remember to change only the sign of the imaginary term to get the conjugate. Multiply the top and bottom of the fraction by this conjugate. From here, we just need to multiply the numerators together and the denominators as well. Use the distributive property when multiplying the binomials. Combine like terms in both the numerator and denominator. That is, combine real numbers with real numbers and imaginary numbers with imaginary numbers. Never forget to replace I squared with minus 1. Perform all necessary simplifications to get the final answer, and do not forget to split the complex valued fraction into its two separate terms. We now will do the same as we did in the previous example. But we should take care because the conjugate complex of 3 times I is minus 3 times I. Remember to change only the sign of the imaginary term to get the conjugate. Multiply the top and bottom of the fraction by this conjugate and perform the calculations. Powers of the imaginary unit. We know that I is equal to square root of minus 1, and I squared is equal to minus 1. We can apply the properties of exponents we know to be true in the real number system, so long as the exponents are integers, to find powers of I. With this in mind, let's find the next 6 powers of I using the properties of exponents. Pay attention. From the table, it appears that the powers of I cycle through the sequence of I, minus 1, minus I, and 1. Therefore, we get a pattern. We will need to remember the powers of 1 through 4 of I to obtain one cycle of the pattern. From that list of values, we can easily determine any other positive integer powers of I. The method is very simple, but we must remember how the division works for integers. The division with remainder is the process of dividing one integer, the dividend, by another, the divisor, in such a way that produces a quotient and the remainder is smaller than the divisor. Let's work out 9 divided by 4. 9 is the dividend, 4 is the divisor, 2 is the quotient, and 1 is the remainder. We can see that 9 is equal to 4 times 2 plus 1. We now will calculate I raised to the power of 9. We replace 9 with 4 times 2 plus 1 and apply the properties of exponents. We can see that I raised to the power of 9 is the same as I raised to the power of the remainder. We will apply this method to calculate I raised to the power of 10. Divide 10 by 4. We see the remainder is 2. Then I raised to the power of 10 is the same as I raised to the power of 2. In short, to calculate the power of I, we divide the original exponent by 4. Then we do I raised to the power of the remainder. Simplify the following powers of I. I raised to the power of 27. At first, we divide 27 by 4. The remainder is 3. So I raised to the power of 27 is the same as I raised to the power of 3. I raised to the power of 137. Divide 137 by 4. The remainder is 1, so I raised to the power of 137 is the same as I raised to the power of 1.